Now we're going to look at Chapter 6, which deals with thermal energy and thermodynamics. So the first thing we need to establish is what we mean when we say temperature. Now everybody has kind of a sense, they understand what temperature is. They think of temperature as being hotness or coldness relative to some temperature scale, whether you're talking about Fahrenheit or Celsius. But temperature is actually the measure of the average kinetic energy of the motion of a body's atoms and molecules. Now, we talked about how, in the last chapter, we talked about how if you have like an enclosed partition with a gas in it, the molecules of the gas are going to be zipping around the box and bouncing off the edges, and that creates the pressure on the walls of the container. Well, the fact that these guys are moving, that means that they have kinetic energy. And if you remember, the formula for kinetic energy is 1/2 the mass times the velocity squared, 1/2 mv squared. And so if these guys, they're molecules, they have a mass, they're moving with some velocity inside the container, they're going to have a temperature. Now, what about a solid or a liquid? Because those are not zipping around the container. If I just have like a lump of gold or something, what's its motion creating kinetic energy? Well, the atoms aren't able to move freely like they could in a gas, but they are able to vibrate. And so they can vibrate back and forth. And as they swing to and fro, back and forth, those vibrations, those atoms and molecules, they have kinetic energy. So if you add up all the kinetic energy of all the atoms and molecules and you divide by the number of atoms and molecules, then what you end up with is the average kinetic energy of all the atoms and molecules together. And that is what we call temperature. Now, when we measure temperature, we generally do it via a temperature scale. And you can see the image over here on the right, we can see the two most common temperature scales used in the world today. There's the Fahrenheit scale, which is used in the United States and not very many other countries, but maybe a few. And then there's the Celsius scale, which is used in most of the rest of the world besides the United States. And we'll talk a little bit more about this as we go. Now, as we said, temperature is related to the motion of atoms and molecules. And it's a per particle property. That is, every particle of the material, it has its motion contributing to the temperature of that material. And we can talk about what we call thermal energy. And thermal energy is related to the total kinetic energy of all the particles of the substance. Now, when we talk about the motion of molecules, which, as you remember, are atoms that are joined together in different configurations, there are different ways that motion is possible. I mentioned that you could have a gas, for example, with a molecule zipping around inside of a box, or we could have a solid or a liquid with the atoms and molecules vibrating back and forth. The zipping back and forth in the box is an example of what we call translational motion. And the vibrational motion, of course, is the other kind of motion. There's actually a third that can be considered. Molecules can spin. They can not only vibrate and translate, they can also rotate. And so all these kinds of motions, the moving back and forth, the vibrating back and forth, and the rotating, all of these can contribute to the thermal energy of the substance. Now, the next concept that I want to mention is something called absolute zero. So let's go back and look at our definition of temperature. Temperature is the average kinetic energy, 1/2 mv squared, of all the atoms and molecules of their motion. And so temperature is related to the motion of atoms/molecules. The faster something moves, the higher its temperature. Because as V gets bigger and bigger, as the velocity goes up, if it's moving faster and faster, the temperature goes up. The reverse of that is that lower temperatures correspond to things slowing down. So what's the slowest that something could possibly be moving? Well, stopping, coming to a dead stop. And so I could imagine I have a molecule in a substance and the atoms are vibrating back and forth. And as it cools off, they go slower and slower. At some point, if they came to a stop, you couldn't go any slower than not moving at all. And so that's the lowest possible temperature that a substance can have. It's the temperature at which all the motion of all the atoms and molecules of the substance comes to a dead stop. That's absolute zero. And it turns out you can't actually get to absolute zero. You can get really, really cold. You can get really, really close to absolute zero, but you can never go there all the way. And the reason for that, as you get, imagine you have a block and you're cooling it down and you're getting it closer and closer to absolute zero. Well, it's going to be in an experiment or something that's at a higher temperature. And as this gets colder and colder, we're going to see that heat will actually flow from the environment into my experiment and spoil my efforts to get all the way to absolute zero. Because as we'll see later, heat always flows from hot objects to cold objects. And so if you're cooling it down, heat's going to want to flow from the warmer objects nearby. That's why you can never actually get to absolute zero. But you can get pretty darn cold. Now, we talked about the Celsius scale and the Fahrenheit scale. There's a third temperature scale, and it's the one that's based on absolute zero. And that's called the Kelvin temperature scale. Now, the distance between Kelvin temperature degrees and Celsius temperature degrees is the same. And I'll explain what I mean by that in just a minute. But let's look at this image showing 3 different thermometers and some common temperatures. So let's start with the Kelvin scale. At absolute zero, the Kelvin scale has 0 as its temperature. That's what we mean when we say the Kelvin temperature scale is based on absolute zero. The 0 on the Kelvin temperature scale is the coldest temperature possible in the universe. On the Celsius scale, the 0 is the freezing point of water. And on the Fahrenheit scale, the freezing point of water is 32 degrees. So that gives you sort of a basis for comparison. The human body temperature, the average human body temperature is 310 Kelvin. And by the way, that's the correct way to say that. You don't say degrees Kelvin, you just say 310 Kelvin. I don't know why, that's just the way it is. But on the Celsius scale, you do say degrees, and so the human body temperature on the Celsius scale would be 37 degrees Celsius. And of course, on the Fahrenheit scale, it's 98.6 on the Fahrenheit scale. We can look at the boiling point of water, 373 on the Kelvin scale, 100 degrees Celsius, and 212 degrees Fahrenheit. Now, when it says the distance between Kelvin degrees and Celsius degrees is the same, what that means is this. So consider the freezing point of water. On the Kelvin scale, it's 273, and then the boiling point up above is 373. The distance between those temperatures is 100 degrees. Now, if you go to the Celsius scale, the freezing point of water is 0 degrees Celsius. The boiling point is 100 degrees Celsius. The difference is, again, 100 degrees. But on the Fahrenheit scale, the difference is different. On the Fahrenheit scale, you have 32 degrees for the freezing point of water and 212 degrees for the boiling point of water. The difference between those two temperatures is 180 degrees. That means the distance between a single Kelvin degree is bigger than the distance between a Fahrenheit degree on the two thermometers. The next thing that we want to look at is heat. Now, a lot of people think that heat and temperature are the same thing. They are not. They are, in fact, very different from one another. Heat is not temperature. Heat is not even thermal energy. What heat is a transfer of thermal energy. And that transfer of thermal energy generally occurs due to a temperature difference. And so objects do not and the not is capitalized to emphasize this, objects do not contain heat. They contain thermal energy. And when that thermal energy flows from one object to another, we call that process heating or cooling, depending on which way the heat is going. But heat is that transfer of thermal energy. It's the transfer of energy, and that is a very, very important thing to keep straight. Now, heat and temperature are different concepts. It is very, very important that we not mix them up. So let's look at our example here. We have a container with water and a hot stove. And what we're seeing here is, so I've got a little bit of water here, and I put my thermometer in, and so the mercury is going to rise up the thermometer, and you're going to see the temperature. Now, we're told in the example, the pot on the left contains 1 liter of water. The pot on the right contains 3 liters of water. Now, if you put them on the stove at the same time and leave them on for the same amount of time, everything is the same size, everything else is the same except how much water is in the container. They're going to receive both the same amount of heat energy transfer. And that's what's going to go into making the temperature of the water go up on the stove. However, the temperature is going to increase 3 times as much in the 1 liter of water than it does in the 3 liters of water. Because you have the heat that's equal on both, but this heat is acting over much smaller amount of mass of water, and so that heat is going to raise the temperature up higher. Whereas here, the heat has to raise the temperature of more matter, that is, get them all vibrating back and forth faster and faster, and so that heat gets used up and spread out over the bigger amount of water. And so the result is that you get 3 times as much temperature increase in the liter of water as you get in the 3 liters of water. So 3 times as much water means 1/3 the temperature increase. Now, heat is a transfer of thermal energy. So that tells us that heat is going to have units of energy units, which are joules. Now, very often, there are other units for heat that are used. Like, for example, we have miles and kilometers in the United States that are used in different areas. And so that's a different kind of distance unit. Well, joules and calories are different kinds of energy units. Calorie is very heat specific. When you're talking about calories, that's generally referring to heat. If you're talking about joules, that's just energy, and it could be any kind of energy, including heat, the transfer of thermal energy. Now, this is the craziest thing, but this is the way it works. When you're talking about calories, we have small c calories, which you can see I've got the word calorie here with a lowercase c. And then we've got big C calories, which is the word calorie here with a capital C. Small c calories are smaller than big C calories. In fact, 1 big C calorie equals 1,000 small c calories. And we say that 1 big C calorie is equal to a kilocalorie. Remember, kilo means 1,000. Kilometer is 1,000 meters. Kilometer. A kilocalorie is 1,000 little c calories, and that's 1 capital C calorie. Okay, we have one of these check our understanding checkpoints. Let's take a look at them. So question 1 says, if you apply a flame to 1 liter of water for a certain time, and its temperature rises by 2 degrees Celsius, if you apply the same flame for the same time to 2 liters of water, that is double the water, how much does the temperature rise? The answer is half as much. Because you're heating up twice as much water, the amount of heat that you're putting into the system is going to be divided by the twice as much amount of matter. And so our answer is going to be 1 degree Celsius. That's going to be how much the temperature changes. The next question asks, if a fast marble hits a random scatter of slow marbles, does the fast marble usually speed up or slow down? Which loses kinetic energy, which gains kinetic energy? The initially fast-moving marble or the initially slow-moving ones? So, you have some marbles and they're moving back and forth kind of slowly, and then you have a really, really fast-moving marble and it comes in and it interacts, it collides with them. And so, when they collide, there's going to be a transfer of energy and a transfer of momentum. What's going to happen is this guy's going to rebound and this guy's going to go that way. And what's going to happen is the slow-moving guy is going to speed up a little bit and the fast-moving guy is going to slow down a little bit. And, as this guy keeps bouncing around these slower-moving molecules, what's going to happen is that he's eventually going to slow down and the rest of them are going to speed up a little bit. And what this has to do with heat transfer is that it's the way that temperature changes can occur. You have the fast-moving molecules and atoms. They hit the slower-moving ones, and so the slower ones speed up and the faster ones slow down. Imagine you have some cool water that you pour into some hot tea. What happens is the cool water interacts with the hot tea. The fast tea-moving molecules, they hit the cool-moving water molecules, and the tea slows down. The tea molecules slow down. The water molecules speed up. And so you get the cooling down of the tea and a warming up of the water. And that'll keep going until they reach some common temperature in the middle.